Thank you so much. This is an awesome presentation. So this one kind of rolls a little bit into, like you guys were talking about as well, of really the importance of being able to understand what your systems are actually doing, and then building out these tool chains, the importance of that, in order to actually develop high quality AI systems. So yeah, gonna dive into this talk on checking what your blind spot is when you're developing perception systems. So just to start us off, we're a lot of people here are working on building this future of self-driving cars. Will be awesome. Great safety implications, better accessibility, tons of benefits. I'm personally excited to be able to drive around, without having to actually drive. Not a big fan of driving myself, to be honest. So really exciting, potential. But it really just the power of what AI can do these days goes way beyond just that. There are studies suggesting that like 85% or 65% of all internet bandwidth is video data. So this notion of visual data just being everywhere is a fact. And it makes sense. Like it's our main sense that we use to perceive the world. So when we want to be able to develop some kind of autonomous system that can take stuff that we have to do and do it for us, it makes sense that we will look at vision first. So lots of applications outside of just automotive vehicles or autonomous vehicles, from retail to healthcare to manufacturing, agriculture, tons of different verticals that are all trying to solve the same problems. And that's really kind of like a key motivation for this talk, is that a lot of the things that you're going to see focused on autonomous vehicles, but these patterns and designs that you see for developing these AI systems spans lots of different industries. So just for reference, I'm a machine learning engineer at FiftyOne, and I'm the customer success team, one of the founding machine learning engineers of the company. And I work, both day to day with working with our enterprise customers across lots of different verticals, just helping them build out these stacks around product, which I'll show you in a little bit. But this is mainly about how to actually set up these best practices to develop whatever visual AI you're trying to build. So for this talk, just going to just briefly an overview of what these AI systems look like. Some folks here are doing this day to day. Some folks may not be that well versed. Then dive into the importance of data engines and these kinds of computer vision toolkits that pretty much everyone needs to build out. And building it out right is really the best way to develop production AI models, and then dig into the challenges that I've seen working with our customers, and then solutions to those. So how do you actually build out these systems at the scale of the types of data and the capabilities of these models that you need to be able to navigate and see? It's a hard problem. So let's dig into this first part. So, what is an autonomous system? It's really just any mechanism where you can take some kind of data from the world and then produce an output of some kind that will, help provide value to us as people. So do something that I don't necessarily want to do. Now, how you actually build those, that can be done in a lot of different ways. But there's tons of different applications to that, from self-driving cars to medical use cases. Everything that I talked about, taking an X-ray as input and then classifying if it's cancerous or benign. It's all kind of a similar idea as taking in sensor inputs from images, LiDAR, IMUs, additional sensors into some system that then produces the controls of your vehicle that will start driving your car. These systems, they don't necessarily need AI. If it's simple, like a calculator, take some input, some output, but there's rules that you can follow. So where does the AI really come in? So this is where computer vision is, again, like vision is our primary sense. And that's also the best use case for AI, because it's really about being able to distill whatever patterns that you have in high dimensional data. And images, made up of millions of pixels, It's a lot of dimensions that you need to be able to reason about. So it's definitely one of the most natural cases to bring in AI systems. So especially as you start talking about different techniques for building these automotive or these autonomous vehicles, there's different ways that you can go about bringing AI into that, from these end-to-end systems that some companies like Wave and others are trying to build towards, where you literally just have one big model where you bring in all the sensors and it produces your car's controls. Basically, right there yet. There's a lot of challenges about that, but I mean that is a valid system that takes in some inputs, produces your outputs. Alternatively, you can go with a more modular approach where you start breaking down those challenges into the perception component, see what's going on in the world, localization, see where you are, plan where your vehicle is going to go. Could try and hard code all of that. That gets difficult when you're working with video streams of a vehicle from multiple cameras, 30 frames per second, with millions of pixels per frame. That's where you really need to be able to incorporate AI in some capacity. So whether it's CNNs, whether it's a kind of transformer-based network, the closer you are to the left side of this, the higher the dimensionality of the data is that you're working with, and the more important it is for you to be able to use machine learning techniques to develop these systems. So for this talk, we're going to be focusing mainly on this modular stack and a perception system. So not necessarily like an end-to-end AI model, though a lot of the same challenges will apply at an even larger scale. But so what this usually looks like is standard perception tasks like an image and then producing some kind of intermediate layer of representation of the world that you can then reason about. So instead of producing the car steering or acceleration outputs, you instead produce a caption about what's happening in the world that you can read about, or detections of where objects are, or tracking objects across videos. There's just some examples of different types of perception tasks. And specifically, we're going to look into what it looks like to develop an object detection model. So tons of things that you can do with this, but this is often one of the first places that you might start. But again, let's do this talk. It's really general for whatever type of AI system we might be building. And that gets us into why data engines are important and what the heck are data engines. So there's a couple of assumptions. One, you have some kind of model that you want to train. So just take your favorite off-the-shelf detection model. You'll have V11 maybe for object detection. You got some data that you want to train on. You have some task in mind that you wanted to do. So object detection on certain types of objects maybe. So let's just say you've got some millions of images in an S3 bucket. Definitely the scales can vary from some hundreds of images to millions of images if you've got a car driving around. And so things start to get tricky. So what do you do from there? Well, you've got a bunch of images, you got a model. 2 million images is a lot. Really need that many to train an object detection model? Maybe not. Also, it gets really expensive when you want to annotate all of that data. So the data curation is often the first step. How do you effectively take 2 million images and find the best 100? And what does best mean? It's in quotes. It's kind of a loaded word. A lot of different applications of how to identify the data that will be most effective in improving your model, from having good distribution across the different types of scenarios that it might have, having high quality data, different techniques that we'll dig into a bit more. Then you need to annotate it. So before you can train your model, you need some examples of where boxes are, so that your model can try and find those boxes. So oftentimes, you'll have to have people that go and draw the boxes, draw the segmentations, generate the ground truth classifications, and then you can train your model. So, oftentimes there's been a ton of work done here. So there's a lot of libraries out there. You can just pip install Linux, train the NOVA model. Great. It'll work to some degree of accuracy. Probably not quite good enough to stick in a car and send it on the road. So that's where this notion of a data engine comes from. So really distilled down, the idea is that you have a model and you want to make it better because it's not good enough for production yet. So how do you do that? Well, after you train your model, you need a way to efficiently identify where your model is failing and why. And then you need to take those insights and you need to improve your data set. So oftentimes, messing around with the model architecture is less important than actually improving the data set itself. So, figuring out that the background is a problem and then improving how you're handling the background of images is often more important than, messing with the model architecture. So what you need to do can vary. It can be things like fixing annotation mistakes, adding more data that will help your model perform better. But you make some improvements, you retrain your model, and then you test it again. You see where it's failing now, and you kind of keep going through this loop. So this, just in general, it's not necessarily a new idea. However, was coined by Andrej Karpathy in just in 2022, which is a little surprising, but at that point in time, that was one of the main selling points of Tesla, was that they had this robust data engine that allowed them to have kind of like a competitive advantage. So these days, a lot of people have their own data engine, but it's really hard to get right. So yeah, just kind of going into that, lots of different references out there. Microsoft has an reference architecture for data engine for AVOps. Definitely want to call out the MCity data engine. It's a great open source implementation of data engine that you can go and try out yourself. Kind of walk through this process of find issues with your model, improve your data set, retrain your model, and then keep going in the loop. To dig into this a little more, I want to just walk through what some of these 3 points might look like. So in the case of object detection, identifying failure modes. Let's take a look at this example. So we've got a bunch of detections around cars and people. It's traffic lights, and then you can see that this purple one here is the model's prediction, and it's thinking that this trunk is a car, which is not great. I don't know how that might affect my downstream systems that are taking this input. But it's probably not what I want, so I'm going to need to do something about that, so that just because there's a trunk open when my car's driving by, it's not going to crash into it or something. So first step is identifying it. Next step is figuring out what to do about that. So in this case, it might be fixing this. Well, it's not really an annotation mistake, so you might want to get more data of cars with trunks open. So this is where improving your data set portion comes in. If there are annotation mistakes, you have to fix those. Garbage in, garbage out. The worse your annotations are, it produces an artificial ceiling on the performance of your model. But it's not always the annotations that are the problem. Sometimes it's the distribution of your data set. So if you've got gaps in the domain of your data set, you'll be able to find those and fill those. So for example, we've got a big gap of cars with their trunks open in this training data set that we need to fill. So we need to get more examples of cars with trunks open, retrain our model, and then reevaluate it. So retraining your model, this is where it gets a little, the best practices come into play here. If you are just naively trying to just get a model trained, it might look something like this. You've got a bunch of images in your file system, you're just, clicking through them, might have some Cocoa labels in a JSON on your desktop, train your model, great. Then you have to do it again to fix it, and then again, and then again. You need to work with somebody else. You need to combine your data sets, keep doing this, and it becomes a nightmare. But to be able to manage all of that, to be able to understand how your data sets were evolving over time. So this is where it's important to be able to have not just a data engine that walks through those steps, but one that does it efficiently, so that you can, click of a button, be able to, for example, version your data sets, trigger a new training job, get those model results into your data set, evaluate them, find where those mistakes are, and then keep doing that. Without that, you're kind of just driving blind. So let's see how you can take the blindfold off in this next section. So what are some of the challenges? Things get especially tricky when you start to scale up to a lot of visual AI use cases that folks are tackling these days, especially in the autonomous vehicle space. If you've got 10 cars in a fleet that are driving around with 30 FPS TV cameras, just one of those give you 10 million or a million images in an hour. That's a lot of data. If you're driving down a highway, it's probably a lot of the same data. You don't really need that much data, but it's coming in. So you need to store it somewhere. You need to figure out how to get the best data out of that. And then you need to annotate it. And that costs a lot of money as well. You know, lots of data, lots of interesting environments. Common numbers that we see are, 10 million. We've seen numbers of $1 billion of annotation budgets that some companies put together for really large projects that they're training. So it's a bit of a problem. We need to figure out a better way to do that. And then also identifying these failures is also tricky because the amount of objects, for example, for an object detection task that you're trying to detect is another order of magnitude more than the amount of images that you've got. So, you might have 10 objects per image. So that's 100 million labels that come in an hour from this fleet. And somehow you need to go through all of that to figure out where the mistakes are. Where is your model performing well? Where is it performing poorly? So that is one of the things that us at Voxel 51 we're working on to help make that easier. So we have a product called FiftyOne, which is designed to kind of serve as the glue to tighten this loop of your data engine, integrating with whatever your stack currently looks like, wherever your data currently is. It's kind of the oil for this data engine, natively integrating with Databricks. Use that for your storage. You can search directly through that. You can do vector search in whatever your vector database is, and then kick off a training job. Goes to any scale or Azure ML, trains your model, integrates with whatever your stack looks like today. If you're tracking your experiments in MLflow, also great. Hook it up to FiftyOne, be able to see directly from your data how was your model trained. So going to dive into a bit of a demo of what some of this actually looks like in practice to make it a bit more real. So going to try and tackle, at least shortly, we're getting a little close on time, a few of these. So for data curation, how do you search through all of that data? How do you find, from billions of samples, what you might be interested in looking at? How do you reduce the amount of human annotation that you need to cut down on the $10 million that you might need to spend to get your data annotated? And then how do you actually evaluate your models to find those mistakes? So let's go ahead and jump over into FiftyOne. So I want to go to a data set that we've got here. This is road scene data set, front-facing camera. We've got images here with some ground truth detections and some model predictions. So you've got some vehicles, and then we've got results from fast CNN. You need to have kind of like a bad model to be able to compare against, and then from a YOLO model to be able to get some predictions from model trained on this data set. So first step is, great, you can see one by one how's your model performing, but it's important to be able to actually dig in and see how it's performing on traffic lights, and quickly be able to filter down your data set to whatever it is that you might want to look at. So for model evaluation specifically, evaluate these model results against the ground truth that we have, and then take a look at what those evaluation results look like. We can compare these models against each other. And this is what a lot of people's model evaluation process looks like. A table of some metrics. You see a model perform better than the last model. A nice line, MLflow. So it's good to know what you do about that. It doesn't really tell you how you should improve the data set just because one model has a better accuracy than another, better MEP. So looking at the different metrics can give you some insights. Things start to get more interesting is being able to look at breaking it down by all of these different strata that you might have on your data set. So whatever that strata is, can you look at the class-wise performance, and this is where things start to get interesting. We can see that fast RCNN is worse performance than YOLO, but it's especially bad and the precision for person detections. What's more interesting than that is both of them are really bad at detecting motorcycles. It's like, why is that? So, some people might already be evaluating like this. It's great. It's a great start. But even with this, still doesn't really tell you why it's bad on motorcycles. So what do you do with this information? Maybe add more motorcycles to your data set. Might be fine. But with FiftyOne, because all of your data is right there, and you can actually visualize it, you can click that cell, and we can go and see what's happening in these samples where these motorcycles are being detected incorrectly. So actually looking into this, you can actually see what's happening. And this intuition is really the key of why we're seeing so much adoption in FiftyOne. Especially when we're working with visual data, in order to know what's happening with your models, you have to actually look at the data itself and see these failure modes. Because just looking at that, I can see what's happening. My ground truth in red here has the person and the motorcycle annotated, but my model is just predicting the motorcycle itself. So it's being flagged as a false positive, which is, probably not what I want. Skewing my evaluation results is going to make it much more difficult to be able to manage this data set. So what can you do about that? One, you could re-annotate your data set. So this is where kind of the interconnectedness of having this data engine becomes important. Being able to go and click on this sample and say, let me re-annotate it. So you probably have an annotation tool that you're using, maybe an annotation partner that you've partnered with. But you can just say request annotations, and I want to re-annotate this. Say we see that. And then I want to re-annotate this truth field. It has detections, and let's just go ahead and send that off, and then boom, we'll send it over to see that. And open up see that, and then I can fix my annotation, bring her right back to FiftyOne, and then now we've got that fixed. In practice, you probably want to tag this as a mistake, keep scrolling through this, find all of the others' mistakes, and then create these annotation tasks in aggregate, and really be able to more quickly identify where your model is performing poorly, and then act on it. So we could hop over here, fix it, hop back. Alternatively, maybe you do want to add more motorcycles to your data set. So that is where the other integrations can come in. So for example, if you've got Databricks Delta table that has a whole bunch of your metadata in it around what images you've got and some of the data that's in there. So I can say, let me query that, go over here and just give me all of the additional samples that I haven't curated into this data set, but that are in my massive data lake that also have motorcycles in them. And then let me actually preview some of that data in FiftyOne. So this is a fully customizable connection to whatever your data source is today that you can hook up and can preview these results. You can query whatever you want. It's all Python based. It's through our plugin ecosystem. So we have this mechanism to build these UIs entirely in Python, almost like Streamlit, to be able to more closely interact with your data. You can see there's a motorcyclist there, motorcyclist over here. A little hard to see, but got some motorcyclists. This looks good. Let's go ahead and import that data and then load these into my data set. And then go ahead and fine tune this model again, kick off an annotation task. This can be backed wherever your compute is today. So in this case, we've got it running on some VMs in GKE. We also have integrations with any scale Databricks if you're using that for compute, just wherever your compute is today, you can hook it up to that. So that's one way that you can kind of interact with your data, see what's going on, and then connect this stack that you have to be able to quickly iterate over your data sets at scale, which is the important part. And then one other thing I wanted to show was for this human feedback, what that looks like. Probably a lot of you are already doing this today, this notion of auto labeling your data. So you don't necessarily need humans to be able to annotate everything. There's a really great off-the-shelf zero-shot models these days from in the case of object detection, like Grounding Dino, the world. might be able to generate an initial set of labels that you could use to some extent. So you can do that as well. So say I've got this data set, no labels in here yet. I can say run a zero-shot model, and then perform zero-shot detection. YOLO world, provide a list of labels, kick that off. I did already run this before and generate some ground truth labels in here. So with no human effort, we have at least an initial set of labels. So these models, they're kind of they're expensive to run. So you're probably not going to want to actually deploy these. You'll want to find your own smaller model that will be able to make use of this training data, but also it's not going to be perfect. So you are going to want to kind of verify these auto labels. So one way that you can do that is through making use of more models to bring into this process. So you can, for example, take every one of these detections that was generated, run, in this case, we ran a clip model on it to generate an embedding vector for each of these object detection patches. And what we're seeing here is a scatter plot where every one of these points corresponds to one of the detection labels that was generated. And the distance between those points is how similar they are. So what we can do is we can color these by whatever attributes we've got. We can say, show me just these labels to the patch view and see just those ground truth labels. And then we can start exploring this. And let's say, look at people. So there's a big cluster of people here. Where things start to get interesting is when you look at some of these outliers. So these are all of the people embedding points in green here. But some of them are pretty far away from this central cluster. So these are most likely going to be your prototypical person detections. The ones out here are going to look a bit different to whatever this model was. It doesn't know why they're different, but it knows that they're different. So looking at these, we can see that, yep, these are just incorrect detections. So this model is off the shelf. It's not going to be perfect, so we can just highlight those, keep that guy, that's person, and then we can say, let's remove these from my data set. And then we can run a job to clean those up if I wanted to. But being able to quickly generate labels automatically, kind of see how well your model performed to generate those labels, and then clean them up so that they are, better than what a model generated. Additionally, if it's only slightly off, it's not totally off, I could then send it to see that and then still get the human in the loop, which is important in order to develop these systems that are better than humans. It's good practice to take the best off-the-shelf models and bring human in the loop. Yes.
Sorry. So how does it track the version of the data if I'm bringing in like corrected annotations?
Great question. Yeah. So that is where I have this notion of like the history of your data set. So before I go in to import some additional data I might have from my data lake, I can say before import. And then create basically a snapshot of my data set that will lock it in like read-only mode in time so that I can always go back and then browse what the state of my data set was in the past. One of our customers, for example, they built their own plugin that at the click of a button sends the data set off to Azure ML, kicks off a training job, creates one of these clones programmatically, and then links those together. So Azure ML didn't have a link to their FiftyOne dataset. FiftyOne didn't have a link to that Azure ML training job. So yeah, basically that's how you can have this connection between datasets and kind of version those as you make changes. Yeah, great question. And I think that is a good stopping point for this. Did get through these couple of challenges, and one way that FiftyOne can kind of help with that. It's a little, didn't get too in the weeds, but the important part is that what you saw here can be hooked into whatever your stack is. And if you don't have a stack yet, that is where like the MCity data loop is a great place to start with fully open source, FiftyOne. Parts of what we're looking at here were the enterprise solution, but some of the core features are available in the open source as well. that can connect, for example, to open source CVAT, which is part of the MCD data loop. You can start to really, kick this off yourself. And with that, I will open up to questions. Yes.
So when you've done the auto labeling and you have a set of labels and you need sort of QA work on those labels, you showed the idea of looking in the embedding space and just sort of auditing the outliers. But is that enough, or don't you have to audit all the data? Because even something central to the embedding space where the cluster is might still be a bad label, right?
Yes. No, you're 100% right. So the outliers is a good place to start looking for potential issues, but definitely you could have problems, even with the central of your cluster detection. So there are a number of other techniques that you can use for that. And in fact, that's one of the features that our team is building out right now. We have a number of ML engineers on our team that are focused actively on this problem of, without having ground truth labels, how do I know how good this auto-generated label actually is? So making, there's some ML techniques that I don't know if I could talk about too much, but a notion of being able to take like embeddings of another model, be able to see as you augment these detections, how does it change? Many other techniques that we're working on to be able to kind of combine these different ways to identify mistakenness of these auto-generated labels. So definitely you want to do more than just look at the outliers, but there's a lot that you can do just due to the flexibility of FiftyOne to be able to make that easier. Yeah, great question. Yes.
I was wondering if there's any way to use FiftyOne or other techniques to identify failure cases before they happen.
Before they happen. Yes, so that is where this kind of notion of being able to combine these models comes in. So being able to actually, that is kind of what we did here with this example where we've got a label that was generated by a model that we haven't actually trained on yet. So being able to use something like the clip model to run on the detection that you generated to give you an idea of if it's a mistake or not, so you can catch that before you go and train your model on it. That's one way that you can do that. Reason being of
I was more wondering about figuring out what kind of data, how you can identify what data you need to gather.
yes, thank you. That was one of the parts that I wanted to show here as well. So yes, you can also use this embedding space to get an idea of what you have in your data set. But that's also where it's important to be able to have just all of your metadata available. So you can generate, for example, a plot of just a new one. So just got all of these different fields on my data set, weather, time of day information. So being able to actually see the distribution of data that you have. So we've got a lot of clear data, not a lot of foggy data. So it's what I've seen work best is a combination of these approaches where you take a look at the distributions of the actual metadata that exists on your data set in a database that you might have, in addition to distribution of where your images lie in an embedding space. So we also have a notion of uniqueness, for example, that works on that embedding space. So it'll provide the scalar value of how unique a sample is based on how close it is to other samples in the embedding space. So a combination of saying, give me the most unique, visually unique samples in combination with a even distribution across whatever of these kind of strata that I might be interested in, making sure I've got a good balance of day and night samples, a good balance of clear samples and snowy samples, or maybe fire up the city snow machine for a view. But yeah, so that would be kind of another technique to really balance out your data distribution. Yes.
I have a question about the space of integrating the data sets for 3D CNNs like slow fast and MM detection to that are like action detection models. Is this platform friendly for these sort of data sets?
Totally, yeah. So really any visual AI use case, we have actually partnered with ActivityNet. So on the website, it's like they recommend using FiftyOne to work with ActivityNet because we do similar to how you can work with 2D object detections, you can add temporal detections, for example, of
Yeah.
an action.
Yes, special temporal models.
Exactly. Yep. So being able to have both like bounding boxes as well as, in this case, it's like a purely 2D example where you've got it approaching an intersection, just turning, so being able to, and same process. So, you've got labels, you've got some model predictions, you can evaluate those in the same way, find, is the class imbalance, find high confidence on false positives. But yeah, so that's fully supported.
Thank you.
So just to make sure it's not for only for object detection, you can just extract failure cases in motion forecasting dataset. Or like I saw new scenes and all of this stuff.
Totally.
So
Yes.
you can extract those failure cases and take those failure cases and use them like whatever you want, right?
Exactly. Yep. So this example of like object detection in images was just one that just wanted to show to kind of simplify things, but to support full sensor modality, LiDAR, radar, view scenes. You've got new scenes for metadata, can do all the same things on that. We've got some customers that are working with like audio detection. So it's really, like all of those use cases that I showed at the beginning, from healthcare to agriculture. We don't really care about what's in your data, what you're doing with it. It's this notion of like efficient data to have a mechanism to find failure modes of your model and improve your data set. That's the important part.
So as long as it's vision data stuff, like even the with the audio data, right? So I mean, you cannot deal with scenario data, for example, like only coordinates and acceleration.
Not as easily. There are ways that you can do that, and you can have like visualizers. For example, if you've got captions, this is something that wasn't built in, but somebody wanted to be able to visualize NLP data, so you can extend the visualization capabilities as well. If there's something that you can't necessarily do yet, but you might be able to use our 3D visualizer to start visualizing some of that in some capacity. But that's where you do all that for free. Pip install FiftyOne and just try it out. Sure.
Can you process video, like, have data points as videos instead of like single frames?
Yes, 100%. So whether you have those videos stored as frames, you can kind of group those together and play them back, or if you've got actual MP4s, you can play them back. Yes.
That's good. For my face.
Oh, yeah.
Facts over here.
Robbie over here together a data set. Somebody was interested in, the in-cabin, facial landmark detection. It's kind of hard to find an off-the-shelf data set of that, so we just went out and
Go to
together.
the first video.
That.
It's like the first one. First one I wrote about it.
Gotcha. Yeah. So being able to play back whatever type of task that you're working on. Yep.
And then you could like one click turn it to frames. I think 30 frames per second or 60 pounds. But that was just done with this iPhone and a $30 car mount.
It's more of like a example, but just the type of data that you might have can bring it in.
Can you compute embeddings on that too?
Absolutely, yeah. So that's where it's important to know that it does hook up to your compute cluster. So if you've got GPUs that you're paying for,
Sure.
you can just hook it up to there, and then you can say, embeddings. Embeds hard. Yeah, so for example, if you want to compute like the embedding visualization, you can do that. If you want to compute like a similarity index and store that in whatever vector database you're using, create integrations with all the big ones. Choose model that you want to run. So, Dino, like whatever model from RZoo, if you've got your own, like that as well to do that. Any other questions? 3, 2, 1. All right.